My name is John Farrier. I work for Booz Allen Hamilton. I do modeling and simulation for a living. I am a generalist. I know very little about many things, and this is one of them, floating point. So I wanted to come today and talk a little bit about some things that I've learned about floating point and kind of prepare everybody else for learning more. This is going to be kind of basics of what floating point are, the vocabulary you need to continue to understand more about floating points. Try to give you a few tools so that you can walk away with something usable, and basically prepare you to learn more as it pertains to whatever it is that you do on a day-to-day basis. It's a pretty full-length talk. If you could, I would appreciate keeping your questions until the end. So if you are concerned about floating point, you are in good company. I like this quote, that nothing brings fear to my heart more than a floating point number. And perhaps after the first few examples, you'll begin to understand why. But I think it's also important as we go through this to keep everything in perspective. As a modeling and simulation person, I like this quote as well, that modeling error is usually several orders of magnitude greater than the floating point error. And people who nonchalantly model the real world and then snare at floating point as just an approximation, well, I think they've got things well out of perspective. So keep that in mind as we're going through this too. This is not the end of the world just because math doesn't actually work like you think it might work. There's a lot of floating point fallacies, at least floating around my office. Every time something seems to be not quite right, I hear it's just floating point error, don't worry about it. There's all sorts of other myth and lore kind of going on about floating point. And I think maybe after this, hopefully we'll be able to talk about things more intelligently and be able to maybe guide our discussions in a productive way to minimize errors that actually do exist. If you were to Google this like I did, all roads lead to Stack Overflow, and every Stack Overflow post will tell you to read this document. This document is 93 pages. It's not exactly a quick answer to whatever question it was you innocently were trying to ask. The first sentence out of the document is that floating point arithmetic is considered an esoteric subject by many people. So now please continue reading for another 93 pages on something that's esoteric and you just had a simple question about. Thank you, Stack Overflow. Please go read this document after my presentation. Let's first talk about the anatomy of a float. There was a time, evidently I wasn't around for it, but prior to 1985 in computing, when hardware vendors implemented things in a very hardware vendor specific way. We don't have that problem anymore today, right? So along came a standard or two or three. So standards were created so that math could be implemented portably between machines, and there was much rejoicing. The standard said some significant mathematical identities should be maintained, and there's a few. The standard also goes in and says there's about 50 functions that should work basically the same on all the hardware. The standard evidently has been a little weak in exactly how to do a lot of those things, so there can still be some anomalies from system to system, but in general, now we have portable math. The goal is to ensure that every floating point number representation is unique, which seems obvious, but this requirement put a special case around 0. Ensure that every floating point number has an opposite. It doesn't do you any good to only do positive math. And then the algorithms that are specified. So there's a few listed, but there's actually, I think, about 50 in the standard. Internally, floating point representation is an approximation using scientific notation. Easy enough. So let's talk about how that actually works. You have a -1 to a sign bit exponent. Then you have some base, in our world it's base 2, to an exponent. And then 1 dot mantissa. Mantissa just being the part that follows the dot. And so if you were to look at the bit representation of that, and print it out with a bit set, you will get something like this. I added the brackets to parse it for you, but that's kind of what you're looking at if you were to use a bit set for a 32-bit float. So 32 bits gets you 1 signed bit, 8 exponent, and 23 mantissa. 64-bit doesn't exactly double things like you might have anticipated. So you actually get a lot more mantissa bits, which ends up being important, because remember, the exponent is only used to kind of scale your number there. There are, of course, special floats. Maybe divide by 0. I don't know if anyone's ever ran into that when you're doing math. I haven't, but I've read about it. Not a number. There's some special situations that get you into not a number conditions. You get signed infinity. The reason we have that is for overflow protection for very large numbers. We have negative infinity for very underflow for very small numbers. We also have positive 0 and negative 0. I'm not going to dwell on these corner cases in this talk, but I think it's worth noting that they're all there. We've probably all ran into them, and you can look up the types of situations that get you into having special floats. So that's floating point layout. And we are, of course, now all experts on how floating point will work. Let's start with a simple example. Possibly it's later in the afternoon, we can do this math in our head. I've got some obscurely named variables, 0.1, 0.2, and 0.3. I'm going to sum those up, and I'm going to do some checks. All this code, I've got some code examples, that's all on GitHub. I've got a lot more examples under the CppCon project. You're welcome to download that. I tested it on one whole compiler once, so I'm sure it'll work fine everywhere. But it gets me data for this briefing. So let's do this in your head real quick. Sum should certainly be 0.3 if we do this in floating point. Neither 0.1 nor 0.2 nor 0.3 were the numbers that we typed in. If you actually print them out, I mean, they're close, but they're not the exact number, and we haven't started doing really, interesting math yet. You may have noticed in the example, though, that was all floats. And we know floats are 32-bit. So being intelligent people, you say, yes, but I'm just going to use a double, and I'm going to fix it, and it will be much better. Well, no, you just end up with a different problem. And now 0.3 does not equal 0.3 anymore. Which may not be what you were anticipating by just increasing your precision. So there's other things going on here, other things at work. Maybe we can understand the storage of 1.0. Let's just start there. How do we store 1.0 in a float? Well, we have a signed bit, we have an exponent, we have a mantissa, so negative 1 to the 0 times 2 to the 0 times 1.0, okay? We need to store, looks like, 3 zeros. That does not quite look like what I would expect for 1.0 in memory. Yeah, it actually looks like this, which isn't quite what we said starting off for the exponent. Why is that? Well, the exponent is, of course, shift 127 encoded. I mean, I'm sure everybody knew that going in. I thought I'd put it on the slide just to clarify, but it's shift 127 encoded. Slightly different than what you may have anticipated going into this. Okay, fine, but that creates our special case for 0. We talked about that up front. 0 is a special case. All zeros is 0. Now, if we want to actually represent something, we've got to shift 127 encode the exponent so that 0 maintains a special case and every floating point number is unique. Okay, great. So now we know how to represent 1.0. Let's toggle that last bit. Go to the next number. All we did is take the 0 on the end, change it to a 1, and we get a much different number. 0 on the end, change it to a 1, much different number. What is the significance of this number? This is epsilon. Epsilon is defined as the difference between 1.0 and the next available floating point number. This is useful for kind of almost equal conditions. As you saw from the 0.3 does not equal 0.3 example, directly comparing floats can be dangerous. Epsilon can help. Check out standard numeric limits. It defines epsilon and a host of other things that we'll be talking about. But then you can find out what that is for your specific system without having to go through this check. Significant digits are basically a measure of precision. And you have to keep in mind when you're figuring out your IEEE floats that you've got all this precision in the mantissa, but in order to compare them, you've got to kind of have exponents that are the same. So significant digits isn't really the magnitude. That can change. The number of significant digits can change based on your exponent. But this is kind of interesting that this is out of a document here that shows we're primarily going to be using single and doubles. You have 6 to 9 digits and 15 to 17 digits of precision, significant digits, not bits of precision. I misspoke because that's right there. Yeah, so even if you can print out lots and lots and lots of decimal places, some of that is going to be noise. Which brings us to maybe how do we store then very, very small things? For a 32-bit float, you have a minimum base 10 exponent of negative 36. Fine. I want to represent a number that's smaller. I go one smaller, 1 to the negative 37th. And how do we represent that? All of a sudden, our exponent field has gone to 0. And this is a special case. This is called a denormalized number. So if you're reading about these and you come across denormalized or denormalized number or denormalization, this is a way to start to gradually fail. Okay, you are running out of bits to work with at this point. And this helps prevent underflow. Okay? It's important to understand that the representation of these numbers, as a result of how they're implemented, is not uniform between all the numbers. All of the precision really lies between 0.0 and 0.1, positive and negative. You've got a lot of precision right there. And the further out you go, precision falls away. There's standard next after, which will tell you what the next number is after the one that you have, which is kind of interesting because it continually return different numbers. On the MSDN site, there was an exercise on this web page, and it's fairly interesting. Go there and look at this, but I believe this was a 6-bit float that they were implementing. And then they plotted the distance between each number, and you get this kind of interesting distribution. This is going to be a different distribution than what we're dealing with the IEEE floats, but it's going to have the same shape. At least I thought it would have the same shape. So wrote a little program to find what the next number is. I counted up all the numbers from 0.0 to 0.1, and there were quite a few. But now going to 0.2 is far less. And then every time I double the distance I'm going, I get that same number. And I only ran this out to 3.2, but you can see how it's scaling. So that when you're doing math, to me, this says it would be very useful to keep math normalized. -1 to 1, you've got a good amount of precision in there, and that's going to help your math out. And when you start dealing with very, very, numbers really that just deviate from -1 to 1, you are losing precision. And make sure that's acceptable to the types of math that you're doing. Which brings us to errors in float. I thought this was an interesting float with an interesting error on it. You never know what you're going to get when you're looking for images to help with your briefing. So let's look at the storage of pi. Pi is a good number, right? If you look at the value of pi represented as a float, it's slightly different from the regular version of pi, and there's a delta there. So what does that delta mean? That is units in last place, right there. There are two very popular definitions out on the web, the Harrison and Goldberg definition. There's 6 to 8 other definitions floating around. I'm not sure there is a definitive definition, but the one I liked because I understood it the most was the gap between two floating point numbers nearest to x, even if x is one of them. So on here, you're looking at 9 units in last place, that being the difference. The standard itself requires that basic math operations are correctly rounded to within 0.5 units in last place, which seems like a very good guarantee. More complex functions, of course, could be rounded to between 0.5 and 1 units in last place. So depending on the kinds of math that you're doing, the kinds of functions that you're using, you're going to get different guarantees on the precision of those functions. Another way to measure error, which I like, especially for unit testing and regression testing and those types of things, is relative error. That is the difference between the real number, the approximated number, divided by the real number. I went ahead and wrote that out because it's kind of hard to say, but it's much easier to see. So if we look at our relative error for this, it's 2.8 to the -8th, which I think helps put that in perspective again on where that error actually lies, how far out is it, and then you can decide, is that good enough for the type of application that you have? There's the one everybody always talks about, which is rounding error. Everything is rounding error. Forget all the other things we talk about. Everybody just calls everything rounding error in my experience. So what is rounding exactly? Well, we have a fundamental limit. That is, we've only got so many bits to fit an infinite number of numbers into. So of course, we're going to have to round at some point. You can't have all of that precision all the time. The universe is only so big. On the CPU, math is done exactly, and then rounded to give it back to you. So there are several rounding modes that can be used. Sometimes these things can be controlled by compiler options. Sometimes you do not have control over them. There tends to be right ways and wrong ways to do this rounding. Sometimes it makes sense, round to the nearest. Round towards 0. You can think on the number line, you're always going to be moving towards 0, whether you're positive or negative. There's also rounding towards infinity and rounding towards negative infinity. There's also a term out there called exactly rounded, which you're welcome to Google, which is quite interesting as well. But what about the halfway case, the 0.5 case? You could round up, you could round down, you could round even. In school, I was always taught 0.5 rounds up to the next number when you're rounding. But that really wouldn't work out well, because now you're going to put a bias into your rounding. Your numbers will tend to grow versus something else that might tend to neutralize that. So that technique is called rounding even. That is, you're going to round to the next even number. So then, statistically, hopefully, half the time you're rounding up, half the time you're rounding down, and over time that cancels each other out to keep your total error from growing. How is that done? Well, there are at least 3 more bits after that last bit that we talked about. The guard bit, the round bit, and the sticky bit. These bits are only used when you're doing calculations. They're not in memory. They're not something that you're going to observe. They help control the precision and help you learn how, or help you decide how to round. And how's that? Well, if the guard bit is 0, round down. It doesn't matter what the other 2 bits are. But if the guard bit is 1, you should round up if the LSB, least significant bit, in the mantissa is 1. So this is the round even. If it's 0, you'll round down. And all the other cases, you round up. If anybody is interested, when you're doing the math and bits are shifted out of scope here, if any of them is 1 passing through the sticky bit will remain 1 for the rest of that calculation. To help with this rounding too, because you're losing bits as they fall off there. Another source of error is significance error. This is a fairly classic example that I have stolen from a lot of other people's work that I'll show you here. There's a classical formula for computing the area of a triangle. And this is an arbitrary triangle, not a right triangle, an arbitrary triangle. And if you were, you've had a class and you wanted to implement this equation, you find this in the book and then you type this in. This isn't hard to type in. You type this in and you're fairly happy with the answer that you get because you'll get an answer out of that. But it is not generally correct for certain types of triangles. Namely triangles when two of the sides are extremely close to the same length. And one side is maybe much smaller than the other two. So there's a book, and I have it in the references, and the title escapes me because I'm presenting in front of a bunch of people. But there's a book on floating point arithmetic. It's blue. What's that? No, because that one's out of print. There's one you can still buy. I don't remember. Not numeric, I don't know. Maybe, well, sure, whatever, numeric algorithms. I know, it's in my notes, it's on the GitHub. Whatever, I'm sorry I brought it up. But Kahn said that there's a way to design this algorithm so you get a much better answer. And the idea in general is that when you're doing arithmetic, you want to keep big things with big things and little things with little things until you can't do that anymore. So that you keep your exponents of similar magnitude together when you're doing your arithmetic. So I went ahead and wrote this up. There's my triangle. A, B, and C, the lengths of the sides. My application that I wrote online that you can grab, it was all done with Google Test so that we can check some things, and it's kind of handy. You can trust that I implemented the two formulas correctly. I'm sure I did. I rarely make mistakes. And let's go ahead and do this math. So first off, we're going to do this math as it's written here with floating point arithmetic. There's the answers. One, typing that equation in out of the book. Another one using the numerical analysis way of typing that algorithm. And those numbers are drastically different. I think you can probably do that in your head, but I went ahead and printed out the delta anyway. There's another problem. So let's go ahead and toggle this over and maybe do it with double precision. And now we get numbers out of both that at least are in the ballpark, but you can see that Kahn's algorithm is much closer when you care about precision to the real result than the classical formula. So these things can be important. They can bite you. I mean, imagine when I go back a slide, if you wrote this test, and you said, well, okay, no, I mean 14.5, sure, that seems like a reasonable number. I mean, nobody jumped up in here and screamed. That's not 14.5. You would do this, you would look at the results of your program and go, yeah, no, this seems reasonable. Great, move on with life. But that double precision was very important here in this case. The real answer here is use stable algorithms. Sometimes this is very hard. And I think it's something that, personally has not been on my radar long enough. That if you can screw up computing the area of a triangle, well, the stuff we do on a daily basis is generally much more complicated than that. I mean, where are we going wrong there? Parentheses can help. If you know that you can keep big numbers with big numbers and little numbers with little numbers, go ahead and group that kind of thing yourself. But ultimately, you have to analyze the algorithms that you're looking at if you really care about the precision and the answers that you're getting. The compiler won't fight you on this. It will not rearrange your math. If it can't prove it would yield the same, that rearranging it wouldn't prove, read the slide? My tongue doesn't work right now. Yes, it won't screw it up if you're explicit. Look back at that Kahn's algorithm example. There's a lot of good proofs online about that too, if you really want to get into that. How did this all come onto my radar? Let me do a practical example here. Modeling and simulation. We're always wanting to mess with time. That's kind of the fundamental thing. We run simulations that progress over time. Time is used in lots of the calculations. Yeah, sure, this is kind of domain specific. Maybe you folks don't care too much about Doppler shift and pulse compression. But for our simulations, we care a lot about those types of things, and they use time. Time is very important. You don't want to screw time up, but how could you screw time up? Because you're just, there's only so many ways to do it. And it's the least, or probably the most, the most trivial of all the calculations that your simulation is going to do. And then, of course, we don't test anything. I mean, that takes a lot of time. What good ever came of that? All it does is ever find bugs and ruin your day. So let's talk about two ways of implementing simulation time that you'll find out there in the wild. Both kind of, I think the first one is kind of the naive first attempt that everybody does if you're just going to write a little simulation. You're going to maybe have the total number of frames that you want to run, or some condition, end condition. The length of your frame, here we're going to be running at 100 hertz, 0.01. And we'll have a little variable that tracks simulation time. Then in our loop, we're just going to keep looping through, and on every loop we're going to do some work and then increment simulation time. Easy enough. Another way of, and that works great for arbitrary time steps. Sometimes you're not guaranteed to always have 100 hertz, and you need to be able to adjust that maybe from frame to frame. So that gives you that ability. It's a good general purpose simulation counter. Then over here you've got delta time, which says I'm just going to track my total frames. I'm going to have a constant frame length. Of course, I should have had const here. Someone will yell at me in this crowd for that. Then I'm just going to say that my simulation time is the total number of frames I have times my frame length, and then a little counter will give me good simulation time. So let's go ahead and run the simulations and just look at our time. Here on the left we have at the top kind of what 1.2 would have been represented as, and then here's what our simulation time really was, and I put the delta below it. Then at 12 seconds, our time was a little bit more off. 120 seconds, it's even more off. By 600 seconds, we're 0.27 seconds off, which is really significant if we think we're running a 100 hertz simulation. Delta time is much better. There's a little bit of noise up front, but then we start getting really consistent results. When I first saw this was kind of, and it was really this case on the left. Simulation we had been using for a long time. And then you start looking and you go, this is not doing at all what I thought it was doing. We've got to do something better. And this is kind of what turned me on to looking more into floats and how to use them properly, so we can get rid of those types of silly errors in our simulations and get on with the real work. So you can imagine my surprise when someone came in and said, yeah, I've got a really, really accurate simulation. It's so accurate, it uses sub-microsecond precision. Sub-microsecond precision, pulse to pulse, we're modeling waveforms. It's fantastic. There's so much precision in our simulation. In the back of my mind, I'm thinking, precision, you keep using that word. So let's come up with the same example. Sub-microsecond precision, come up with an arbitrary frame rate. Here, our delta frame will be 1.2345 microseconds, which comes out to about 810,000 hertz. Pretty quick. So, we know that when our simulation time should be 0.012345 seconds, that clock that they had was actually at 0.01481 seconds. Run out to 12.345 seconds, their clock is now behind. So it started out ahead and moved to be behind because they're accumulating sim time with a floating point. The floating point's fine. I don't need that many more decimals of precision. We've already talked about this, right? Just use floats. It's faster, I'm told. So, should you not use floats? Well, you can always use integers. Integers are very fast. They tend to have a trade-off right here for precision and range. You can still do input and output with floats, so you're only exposing that to your user. If you've got input files or reports that you're writing, do the conversions then. I'm told, I don't write financial applications, but I'm told that financial applications tend to do that type of thing, which makes sense. The other route you can go is to go the software route, right? Use a math library. It might be slower, but it might give you a lot more control. And there's math libraries out there to help with this. I mean, you're not alone if you really care about high precision math. There's some good libraries out there. There's some things in Boost which you may already even be using to help out with this as well. One of our solutions internally has just been to keep simulation time tracked as an int64t or uint64t, which tends to give us plenty of time to run our simulations. We don't tend to project out more than 500,000 years or so. There's other kinds of errors too. Mathematical identities. We learned these in grade school. These are simple. You probably use them all the time to optimize cache numbers, keep them together, whatever. They don't necessarily apply. Distributive rule does not apply. The associative rule does not apply. You change the location of these parentheses, you could get a different answer. You cannot interchange division and multiplication. You can try, but you'll get different answers. How bad could it be? There's a really nice paper on the Microsoft website, paper tutorial, great explanation here of assumptions that the compiler may or may not be making. It's long, and it doesn't talk about anything other than the Microsoft compiler, but I think it might give you insight into how other compilers are thinking about these types of things as well. So let's look at another example. Let's take a radian. We're going to multiply it times 1 to the negative 10th, and then divide it by 1 to the 10th. We know what number we should get out of it. That's our control. And how different could they be? I'm kind of surprised. It's quite a bit different. Mathematically, you know that they're identical. You know that they're identical. But practically, you do get different results with that. Going through all this, there are floating point exceptions that you can use. I like these. It's been more than one time when I am at the end of a calculation and I have NAND sitting in front of me. And I don't know where the hell that came from, because there were 5 million computations ahead of time. Floating point exceptions can make your life better. They can be triggered when you get underflow and overflow and divide by 0. Invalid computations. You can turn these on, you get a nice breakpoint, and it's much easier to then debug those things. You can also start to tune the floating point environment and understand more about that with this little header down here. I haven't dug into that much. I don't want to try to mess with more things than I have to. And there's a lot of other kinds of errors we could talk about as well. I'm not going to get into all of these, other than if you weren't aware, in our C++ domain, the type narrowing and widening rules, you're going to be promoting floats to doubles if doubles are involved, and they won't be demoted unless you're storing it back into a float. So that's something to keep in mind. I would suggest, though, if you care a lot about the math, then to just keep it in doubles and not worry about types. Just use the correct types when you can. Okay, I've got a few other miscellaneous notes I want to go over. Things to take away. One is to please use your compiler's output. It's trying to help. Don't turn off the warnings. Okay, conversion from double to float, just letting you know you might be losing something. Something's going to fall off the end there. There's only so much we can do. Overflow, that might be important if you're going to keep using that number for anything. Truncation, absolutely. And that your numbers might even exceed the range that can be represented. They're great warnings. Please heed them. There's also a technique called fuse, multiply, add. You can look it up on the Wikipedia page there. It's supported by some architectures, but not universally. But this gets you 1 rounding instead of 2 roundings in this type of situation. There's a GCC compiler option to turn it on. There's a pragma in Visual Studio. It's not something I have used, but I wanted to make everyone aware of it. SSE can help as well. I think if you're performance conscious, you're probably already aware of SSE and using it. Unfortunately, C, C++, and Fortran don't have native support for it, but there is compiler-specific support for it, which is worth looking at. I am not aware of what the rules are for SSE math, though, relating to the IEEE floating point standard. So that would be something else that I think would require investigation if you were to look at that. There are a lot of floating point tricks out there. This is an approximation of a famous trick in Quakes library. I would encourage you to look that up, even while you're sitting here, and read the comments. It's much more entertaining than this one. But because of the storage, it lends itself to some silly tricks, which I don't fully understand, but I trust that they tend to work. Finally, testing. You must test. You must design for numeric stability. We looked at that with the algorithms. If changing parentheses, location of parentheses, in a string of addition impacts the result of the math that you're doing, holy crap, right? I mean, there's so much more that you're doing, sines, cosines, inverses, whatevers, and multiplications and square roots, and it's all creating little issues, and it's all going to sum up. And if you really care a lot about your mathematical result, you're going to look at that. Meaningful testing. Don't let that 14.5 value pass in your test. Put some controls in, do something by hand maybe, and figure out what it is that you should be looking for. Documentation, I think, is important. Even just documenting your assumptions, what you think should be happening here, so if it turns out to be a problem later, that there's traceability. There's also a technique worth looking at called backwards error analysis, to say, are the outputs identical for slightly modified inputs? What are you expecting there? And this might help shed some light on whether or not your algorithms are stable. So, that is what I have. I've provided an XKCD comic because everybody loves this, and if you don't understand it, I've also included that as well, so then you can laugh after everybody else. So, that is the end of my talk. I'd be happy to take some questions. Yeah. I don't have an example. There are examples out there that you can find fairly easily. I think if you've got your epsilon value, there are, I believe, C macros for FLT underscore epsilon and DBL underscore epsilon. And there's also the C++ epsilons defined in the numeric limits. What you would do is look at, subtract two numbers, take the absolute value of that, and see if it's greater than epsilon. So that would be one way to use epsilon in your application to compare two floats for equality. Does that make sense? Well, no, you would subtract A from B, take the absolute value of that, and see if it's greater than epsilon. So, so 3 and 4 would not be, or less than epsilon. I'm sorry. Yes. I don't think epsilon does not scale that way. Yes, that's true. Epsilon does not scale. Epsilon is really 1 and the next number. So that is the technique we talked. He said you have to divide the two numbers and compare that to epsilon. But that's the technique we talked about for relative error. Yeah. Yes.
On slide 49, you said that the commutative property didn't hold, but I thought earlier you said IEEE at least required commutative.
Well, let's see. Slide 49 here. So, right. So this says you're talking about right. Those two properties.
Or is that also out the window?
I didn't hear the last bit of that. Actually, I don't know. What did I say up here up front? That's way back. storage of 1. Wasn't there.
Yeah, up here, x plus y equals y plus x.
Yeah. Well, I don't know. I don't know. These are the ones that I found. And you know, there's not too many. And this isn't the same as x plus y plus z.
Right, of course, that would be associated.
Right.
I know that.
Yeah. Yeah. I don't know. Yes.
You said that multiplication is not the same as division. Of course, not the same, but you know what I mean.
Yes.
Is one better than the other in general, or is it just a...
Yeah, so the question is, if multiplication and division cannot be interchanged, then is one better than the other? My understanding is that multiplication tends to be better than division. Practically speaking, that's what I have seen. But I don't know that it is a hard and fast rule that that's the case. For me, the default is multiplication. Yes. Yes.
Just to comment on that, it depends on whether better is defined as more precise or faster.
Sure.
The thing that loses precision is computing an inverse as well as the operation. So if you can remove an inverse either by doing division or by doing multiplication, you can save precision. Multiplication is dramatically faster than division to execute.
Yeah, so the comment is that multiplication is faster than division. So you may need to wonder if you're optimizing for precision or speed, because that may not be the same answer. Yes. Yes.
This was the book that you mentioned, Hacker's Delight.
I did mention that on a slide.
So this is the one in case you're interested.
Yeah, that's got a lot of interesting float tricks in it and other types of things. Yes. Hacker's Delight. Yes, sir. X divided by 0 is, okay. Okay. Man, you were taking really good notes. I should have like showed this to you before I stood here in front of all the YouTubes and stuff to give the. Oh, okay. Excellent. So the FP contract pragma that I showed, I had the parameter backwards. Yes. Yes, and that link that I had on, that's the comment about FMA only being supported on certain hardware. And there's a list of supported hardware on that link that I provided. Mm. That's a good comment. So that the comment there was that denormalized numbers tend to make your code slower. You said 2 orders of magnitude slower that you've seen? Okay, excellent. Very good, very good. Yes, sir. I'm sorry, I couldn't hear you. Oh, okay, great. So there were some articles about how to use Epsilon properly. I'd say I think the Google test library does use it. We tend to not use it and look at relative error and just measure it. So that's kind of what we're doing inside our code. Yes?
So Google Test does not use Epsilon.
Okay.
It uses difference of 4 binary rules.
Okay.
I only know because I had exactly that problem
Oh, fantastic. So it's using the units in last place.
It casts them all to unsigned, adds one, subtracts those for the difference, or multiplies that then by 4.
Great. Then I have no practical examples to offer you, sir, for where epsilon is being used. Yes. Yes.
There is a movement to try to bring it in, right, because there's a huge committee at C that's been trying to add it as well. I wonder if you have any comments as to which parts of it, part 1, 2, 3, the new type stuff that we're thinking about, that would be more appropriate for inclusion in the C++. I don't envision the whole thing will be useful. I'd like to hear your thoughts.
Yeah, so the comment is that C++ does not officially support the IEEE floating point standard. And if it were to support that standard, what do I think? I don't think my opinion matters. But I do have the mic. That's a good point. But I think it kind of goes back to your point as well, that sometimes people want speed and sometimes people want precision, and that those two things tend to fight each other. I had some discussions with folks that were doing stuff on GPUs, and they wanted lots and lots of floats. They didn't care so much about the doubles because that was good enough for the games that they were working on. They didn't need the double precision. Where other people really need the double precision because they're using it for scientific computing. So I don't know how you decide which way to go with that, other than maybe to make it some type of compile time option, whether you tend to want the fast stuff or you tend to want the conformant stuff. There are flags for that now. I don't know how conformant that makes things. I can tell you that in the CMake project I set up for this code, I did have a drop down in there for whether for the floating point option on Visual Studio, and I think there's 3 of them, and you can pick one. And that depending on how you've got that option set, these numbers change. Some tests pass, some tests fail, and all the stuff that these tests were doing is very trivial. So that's kind of interesting that even with this trivial math, changing those compiler flags gives you different numerical results, let alone doing something complicated and important. Anything else? Great, thank you very much.